Hello everyone, this is Ramji Sharma. Let's look at the discontinuities of a function. In this video, we will find the points of discontinuity of a rational function and the point of discontinuity of a piecewise defined function. Okay, so let's look at our first example. In this example, we're finding the points of discontinuities of the function, which is given by this formula here. So we have f of x equals x squared minus 5x plus 6, and we got to find the points or the values of x where this function is discontinuous. Graphically speaking, we're finding the points where this function has breaks or holes or vertical asymptotes. Since this is a quadratic function which is a member of a polynomial function, this function is always going to be smooth throughout the life of this function, meaning throughout the domain of this function, which is the set of all the real numbers from negative infinity to infinity. So in this case, there are no points of discontinuities. This is a continuous function everywhere. So the answer to this question for the points of discontinuity, the answer is none. Next, here we have a function, so we got to find the points of discontinuity of the function f of x equals 1 over x. So f of x equals 1 over x. Now, oftentimes, while we are searching for the discontinuities of the function, we are looking for the places where the denominator equals 0, or the quantity inside the radical is negative. So these are the two things we are constantly looking, and there are a few other places where we will look at, but for now let's just look at the place where the denominator equals to 0, because when you have a 0 in the denominator, then the quantity or the expression or the function is undefined. So where is the value of x where this denominator is going to be 0? Well, one way to do that is just set the denominator itself equal to 0 and solve it for x. Now this one luckily is already solved for x. So x equals 0 itself is the point of discontinuity. Now everywhere else this function does not have a problem, because we are not going to have a square root anywhere, and this is the only place where the denominator is going to be 0. So just try to avoid these two cases for the few problems that we are presenting here. Next example. So these are rational functions, and we're finding the points of discontinuities. The first one is f of x equals x plus 5 over x minus 3, and the question is to find the points of discontinuities of the function f of x equals that. So again, we don't want the 0 in the denominator. That's number one priority, and the other thing we don't want is the square root of a negative. We don't have a square root here, so we don't have to worry about that, but we do have the denominator, so because this is a rational function. So let's find the solution for this equation where the denominator equals to 0. In this case, we have x minus 3 equals to 0, and if you solve it for x, just add 3 to both sides, then you have x equals 3. So x equals 3 is the point where this function is discontinuous. Everywhere else this function is going to be continuous, because there is no 0 other than at x equals 3. Now you should be able to see it without even going that far. Just look at the value of x which will make the denominator equals to 0, and that's always going to be that number there. if you have a simple situation like this. You can pause this video for a while and then look at the answer for the second question. So try to solve it on your own and then come back here and compare your answer. Alright, so I hope you tried it, and let's see if you got the right answer. I'm sure you did, but let's check. So f of x equals x squared minus 9 over x minus 3. Again, we're trying to avoid the 0 in the denominator. So set the denominator equals to 0. So x minus 3 equals to 0, and then solve it by adding 3 to both sides. So x equals 3 is the point of discontinuity. So what is the difference between these two examples where both of them have the same answer? Well, in the first case, we have a vertical asymptote for this function at x equals 3. And this type of case is called the Infinity Discontinuity in calculus, where the function goes to positive and negative infinity as x approaches 3 from both sides in the limit. On this one, however, you can avoid 0 in the denominator if you factor the common factors, as we most often do in finding the limit of this function. So in that case, if you factor the numerator, it's going to become, let's use a different color pen, so this is not part of the answer, so just extra information. That's why I just want to separate it from the main answer. So x minus 3, x plus 3, and in the denominator you have x minus 3, so you can cancel those two, and then you got x plus 3, which is a linear function. So you can avoid the 0 in the denominator in the limiting process. Now remember, you cannot cancel a 0 by 0. So this is true if x is not equal to 3. Otherwise you are canceling 0 by 0, and division by 0 is not allowed. So in the limit you can do that. So you can avoid the 0 in the denominator by redefining the function at exactly x equals 3, and then make it continuous. So this thing is repairable. You can repair the discontinuity, and this function right here has a hole in the graph of this function. So if you look at this, if you draw this function in your calculator, you don't even notice any discontinuity in this function. So let me try to show you that. So here we have, so let's turn this calculator on and then clear the stuffs from there. So I'm going to enter this expression x squared minus 9 over x minus 3 into the calculator by pressing y equals editor, and I have the xy, xt, theta, n here. So let's just press that to evoke the variable x, and then I have a square there, so x squared, and then minus 9, and I gotta divide this whole thing by x minus 3, so I have to insert the parentheses right before x. So let's insert that parentheses here, so hopefully I can do that. So x squared minus 9 divided by x minus 3, so x minus 3. I hope you know how to do this. If not, you might want to look at the manual for the TI calculator or the graphing calculator that you have. So let's just graph it. First of all, enter this and then graph this thing. So as you see, there is no problem around x equals 3. So right here, let me change the scaling here. So if I go to the Windows, I guess I can make it a little bit clear here. So it's gonna be 0 to 3, well, let's make it 4, and then just leave the other parts as they are. So as you see, there's no trouble around this 3. So 1, 2, 3. That's because this calculator does not have that many pixels to show that little hole in the graph. But really, if we are to draw the picture of this function by hand, the picture of this graph, the graph of this function, is gonna look like, because this is gonna turn into x plus 3, so it's got the vertical asymptote at 3, and let's just change the color here. So it goes like this. So this is 1. Well, I think I have to draw it a little bit from further up. So there is this 1, 2, 3, 4, and then 1, 2, 3. So this function goes through 3 with a slope of 1. So I think I'm gonna be okay this time. So right here, okay, let's redraw this one more time. Sorry, because I meant to draw a hole at exactly x equals 3. So it keeps on moving, and then there is a little hole right here, and then keeps on moving further to the right. So that's how it goes. I mean, it's a straight line. Forgive for me not being able to draw it like a straight line, but anyway, that's what happens here. So of course you can skip this part of the video because it's a little bit beyond the scope of this problem, but it is worth mentioning it here. Alright, so let's go back and change the color to black, the standard color. Okay, next let's look at a couple of more examples on this slide, and then we'll have a few more examples later. This one, you're going to find the points of discontinuity of the function f of x equals square root of 2x minus 5. So part A is f of x equals square root of 2x minus 5. So here we don't have the fraction, but we do have the square root, and we cannot have the quantity inside the square root negative. So we gotta find the place where this quantity is going to be negative, and that's going to be this inequality 2x minus 5 less than 0. So that's when this becomes negative, and we got to solve this inequality. So to solve this, we got to isolate x, so just add 5 to both sides. So you got 2x less than 5, and then divide by 2, and then you have x less than 5 half, which is x is less than 2.5. So for those, all the values of x where x is less than 2.5, this function is discontinuous. So this is not just one point. This is actually in the question there are options, so either one point or several points, but in this case it's going to be infinitely many points here. It's the set of all the points to the left of 2.5 where this function is discontinuous, and everywhere else this function is continuous. So again, remember, when you have the square root, the way to solve this types of problems is to set the quantity inside the radical less than 0 and solve that inequality for x, and then you're going to end up with an inequality as an answer instead of x equals a particular value. Alright, you can pause this video here and then work on the second part of the problem. Okay, back to the second part of the problem here. So we have f of x equals 2x over square root of 2x minus 5. Well, in this case, you have two situations here. One, there is a fraction, and the other, there is a radical. The fraction means you have to avoid the 0 in the denominator, and the radical means you have to avoid the negative inside the radical. So to avoid the negative inside the radical, as we saw in the previous case, because it's the same expression, you will have x less than 2.5. So one case is x is less than 2.5. But that only solves the case when this quantity inside the radical is strictly negative. But in this case, we cannot even have a 0 for this whole thing, because the square root of 0 is also 0. So the other case you have to avoid is 2x minus 5 equals 0. Now you can solve this do this both the cases together by solving the loose inequality less than or equal sign here. So if you add less than or equal sign there, and less than or equal sign there, and less than or equal sign there, and less than or equal sign here, you end up with less than or equal sign there, and that's going to be your answer. So that should be it, but you can also write the answers in the interval notation. So if you remember how to write the inequalities into the line graph in the interval, all that type of things, open rays, all that you learned in college algebra, this is going to be the left side infinity, and then, well, in the previous case we had the strict inequality, so that was 2.5, but in this case right here, so this was I did that for the second part, but the first part did not have the inequality, so the equality, so that's the answer. For this one you have negative infinity to 2.5 inclusive, so the inclusive is the square bracket and the exclusive is the open parenthesis. Again, something you don't worry for this problem, but something you need in other cases. Alright, here we have a set of piecewise defined function, and we got to find the point of discontinuity for this function. So in this case it's a piecewise defined function. So part A is going to be f of x equals this value. So let me not rewrite this thing because it's got some other stuffs I gotta fit in here. Now I have to do a little bit of theory here, because this has to do with the main definition of the continuity of a function. So in the previous case, what we did was, in this case we did not even think about the definition of the continuity of a function. We just try to avoid the unusual cases where we avoided the 0 in the denominator in this case, and then the square root of a negative there. But none of them are present here, so none of those things will work on this first part, even though the second part has a square root. So in this case we have to recall the definition of the continuity of a function. So let me rewrite the definition of the continuity of a function. A function f of x is continuous, y equals f of x rather, or a function f if you want to write it that way. A function f of x is continuous at a point x equals a if all of the three conditions are true. The first one is limit x goes to a minus f of x equals limit x goes to a plus f of x. The second, so this is the left hand limit equals to right hand limit. Second condition is f of a exists, meaning it is not something divided by 0 or 0 over 0 or square root of a negative, those kinds of things. And the third one is, so I can say this is part 1, this is part 2, and the third case is that part 1 equals part 2. What I mean by that is that all of these quantities are equal. Now these two quantities, if you recall from the video where I was talking about the limit of a function, this is gonna give me the limit. So this is really the limit x goes to a f of x. So and the second one is the value of the function. So in short, you can think of this as in short, limit x goes to a f of x equals f of a. So the limit equals the value. If that is the case, then the function is continuous. Now if one of the equality is not true, then the limit, I mean, maybe the limit does not exist, maybe the value of the function does not exist, or something combined all together, then the function is not continuous. If the function is not continuous, then we call the function discontinuous. So we gotta figure out where these things happen here. So I'm gonna keep this part on this side while I'm working on this left side. So on the first example here, I have to find the limits and then the values. So where do I find the limits and where do I find the values? Because the x equals a thing here is not clear on this problem. So what we do is look at the possible values of x where the discontinuities may occur. So some of the possible values here are that those values of x where the branches are connected. So one of the connection here is at x equals 0, because on the left side of x equals 0 you have x minus 1, and on the right side of 0 you have x equals 3x minus 1 as the second branch. So we just look at this point. So we just look at x equals 0 as one of the potential points. Now other points are not the problems, because this branch right here is a continuous function. It's a linear function, so linear functions are always continuous. The second branch is also a continuous function because this is again a linear function. So there should not be a problem anywhere else except for the point where there is a connection between these two branches. So we just look at the limits and the value at x equals 0. So at x equals 0, so we're looking at part A of this problem. Limit x goes to 0 minus f of x. So again the left hand limit, so let me clear this thing from here so we can see this function a little better. So we have the left hand limit at x equals to 0. That means limit x goes to 0 minus f of x, and remember what this means is x is less than 0 in this case. So we're in the first branch, so that's going to be the direct substitution because there's no square root, no fraction, so it's going to be 0 minus 1, which is going to be negative 1. Similarly, let's look at limit x goes to 0 plus f of x, which is going to be limit x goes to 0 plus, and that means here x is greater than 0, so we're looking at the second branch, so that's going to be 3x minus 1, and that is going to be, okay, 3x minus 1, that's going to be 3 times 0 minus 1, 3 times 0 minus 1, which is going to be negative 1. So we got the left hand limit as negative 1, the right hand limit also as negative 1. Let's find the value of the function. So the value of the function f at 0, so we're looking at the branch where the equality is involved, and that's the second branch, so we're just replacing x by 0 in this case, so that's going to be 3 times 0 minus 1, which is going to be again negative 1. So all of these three quantities are equal, and that's exactly what I said here. So at 0 this function is continuous, and of course everywhere else this function is continuous. So this function is continuous at every single real number, so there is no discontinuities of this function. So the answer to the first part is none, because there are no points of discontinuity of this function. Now pause this video and work on the second example. Alright, back to the second problem here. So we have f of x with the two branches. So the first branch is square root of x for x less than 1, and the second branch is 3x minus 1 for x greater than 1. Now square root cannot be negative, the square root cannot have a negative quantity inside the radical. So this thing is square root of x less than 1. We already know this function cannot have the values of x less than 0. So that's already one answer from the first branch. Now at the junction, meaning the connection point at 1, so at x equals 1, let's check the left hand limit, right hand limit, and the value. Here we didn't have to check that because we already know the fact that you cannot have a negative inside the radical. So at 1, let's find the limit x goes to negative 1 from the left, f of x. So that is the square root of square root of 1. Now remember, 1 minus is not negative 1, it's just the direction of x, so that's going to be 1. Similarly, let's look at x, limit x goes to 1 plus f of x. So this time the value of x is greater than 1, so it's going to be 3 times 1 minus 1. We're looking at the second branch, and that's going to be 3 minus 1, which is a 2. So as you clearly see, the left hand limit is not equals to right hand limit, let alone the value of the function. So we don't have to go any further than this. You can already mention that since these two values are not equal, so you can say that x equals 1 is another point of discontinuity. So how many points of discontinuity is for part B? For part B, we have 1 point here, and we have infinitely many points coming from the first analysis. So we have this, so we have negative infinity to 0 excluding 0, and then we have this one single point here. Now this type of notation is not required for now, but something you may recall from college algebra on this one. If you don't recall this, that's okay. Just leave your answers as this and that. Now our last example in this video is this, where we have 3 parts and we have to find the points of discontinuity of this function. So if you look at this function, it has 3 parts: x minus 4, negative 4, and 7x. Each piece is continuous on its own because these are linear functions or constant functions, so there is no trouble in their lifetime. But only trouble that can arise here is at the points where this function changes the branches. So one of the points is x equals 0 and the other point is x equals 2. How do I get x equals 0 and x equals 2? Because I have these numbers here. These are the only 2 numbers I have where the function changes the definition. So we're gonna check at those 2 points. So at x equals 0, let's look at the left hand limit. Limit x goes to 0 minus f of x, which is going to be our first branch, because in this case x is less than 0. So the first branch we have x minus 4, so that's going to be 0 minus 4, which is going to be negative 4. The right hand limit is limit x goes to 0 plus f of x, and we're going to look at the second branch because this time x is to the right side of 0, so x is to the right side of 0 here. So we're looking at the second branch in this case. So we have negative 4 for that value because there is no x to be replaced by anything. And the value of the function at 0, which is f of 0, So the equality is involved in the second branch. Let me clear this stuff from here so you can see this thing. So the equality is involved in the second branch, and that's why we're going to take the second branch, which is of course -4. So as you see, all three numbers are equal, so at 0 there is no trouble. So x equals 0 is not the answer. We're trying to avoid, or we're trying to eliminate all the possible cases. So this one possibility is gone. There is no chance that the function is discontinuous at x equals 0. Even though you saw this function has pieces here at 0, even though you saw that the branches behave differently, but there is a connection at 0. Now pause this video for a while and work on the second part of this function, where you're going to check the discontinuity at x equals 2, which is the second connection point. Alright, back to this problem. I hope you worked on this one and you found your answer. So let's check your answer with my answer. So for the second part, we have limit x goes to 2 minus, because we're going to find three different things. So the left hand limit, right hand limit, and the value of the function. So the left hand limit at x equals to 2 is limit x goes to 2 minus and f of x, and so this time x is less than 2, which means we are in the second branch here. We are still in the second branch. So the value of this function after replacing x by 2 is still going to be -4, because there is no x involved. Similarly, the right hand limit, limit x goes to 2 plus f of x, is going to be on the right side of 2, so that means x is greater than 2. So we're looking at this last branch, which is 7x. So we're going to replace x by 2, because this is a polynomial, I mean a linear function, so the direct substitution works, and that's a 14. Now you already noticed here that -4 and 14 are not equal, so we don't need to go and find the value of the function at 2. So it's not worth finding the value at 2, even though you could find it, which is of course -4 if you like, but that's not required. You don't have to go that far. You can already conclude that this function is discontinuous at x equals 2, because the left hand limit is not equal to right hand limit. So x equals 2 is the only answer in this case. So you might be confused with this rectangle here, so let me just clear that. So the one inside the rectangle is the answer. Alright, that is all I have for this video regarding the discontinuity of a function. I hope you learned something out of this video. I will see you in the next video. Thank you for watching. Bye.